Assalamualaikum. My name is Akila Anani binti Saifah Anwar and my student ID is 2024260672.
Hi, my name is Siti Roshafika binti Muhammad Hanif and my student ID is 2024441946.
Assalamualaikum. My name is Nuri Ifa binti Ahmad Kamizi. My student ID is 2024276042. Hi, my name is Raj Sofia Batusha binti Raj Saifrizan and my student ID is 2024691064.
First and foremost, I will start with the introductions. Shikimic acid is a naturally occurring organic compound that can be found in plants and microorganisms. Did you know that star anise, or the scientific name is Elysium verum, is known as one of the richest natural sources of shikimic acid? This compound plays an important role in the shikimic pathway, which is responsible for producing aromatic amino acids such as phenylalanine, triosine, and tryptophans. Because of its important biological functions, shikimic acid has become a significant subject of biochemistry and pharmaceutical sciences. Okay, next we go with the chemical structure of shikimic acid. They contain cyclohexene ring with the three functional group, which is carboxylic acid group, alkene group, and 3-hydroxyl group.
Now, we're talking about physical and chemical properties. Let's discuss its thermal properties. According to literature, pure shikimic acid has a relatively high melting point of approximately 185 degrees Celsius to 190 degrees Celsius. This high melting point is due to strong intermolecular hydrogen bonding within its crystal lattice. However, if you look up its boiling point, you will find that it does not have a standard one. Instead, it is predicted to theoretically boil around 1400 degrees Celsius, but in reality, it undergoes thermal degradation long before it can reach that temperature. This brings us to a fascinating question. Why does it degrade instead of boiling? The answer lies within its highly reactive functional groups. Shikimic acid possesses one carboxyl group and 3 hydroxyl groups attached to a single cyclohexene ring. So, when the shikimic acid is exposed to high heat, these 3 functional groups will undergo drastic chemical transformation. First, we have decarbosylation. Decarbosylation where the carboxyl group breaks away, releasing carbon dioxide gas. And the second one we have dehydration. Dehydration where the hydroxyl groups react with neighboring hydrogen atoms and leave the molecule as water vapor. And aromatization, as it loses these groups, the flexible ring permanently rearranges into a highly stable benzene-like aromatic ring. Essentially, the heat forces the molecule to chemically destroy itself and transform into a completely different compound before it ever gets the chance to boil. At room temperature, shikimic acid exists strictly as a stable crystalline solid. In its pure, isolated form, it appears as a clear white crystalline substance. It is worth noting that the molecule itself does not absorb visible light or glow under UV light. In a laboratory setting, researchers must use specific chemical sprays to make it visible, which can turn it green, yellow, or white against a blue background.
One of the chemical reactions of shikimic acid is biological phosphorylation. This is the 5th step of the 7-step shikimic pathway, which is essential for the biosynthesis of aromatic amino acid in plant, bacteria, and fungi. The chemical equation is shikimic will react with ATP and then it will produce shikimic 3-phosphate plus ADP. This reaction is catalyzed by the enzyme shikimic kinase and involves the specific transfer of a phosphate group from ATP to the 3-hydroxyl group of shikimic. The second one is chemical esterification. In industrial and laboratory setting, shikimic acid is frequently converted into an ester as a starting point for synthesizing pharmaceutical compound like oseltamivir phosphate or known as Tamiflu. The chemical reaction is shikimic acid plus ethanol thionyl chloride or known as SOCl2, and then it will produce shikimic acid ethyl ester. And then the last reaction is known as catalyzation. This reaction is a common synthetic modification used to protect specific functional group on the shikimic acid backbone during the production of complex drugs. The chemical equation is shikimic acid will react with 3-pentanone and p-toluene sulfonic acid, and then it will produce kettle. Shikimic acid contains a 3,4-diol or 2 adjacent hydroxyl group. In the synthesis of oseltamivir, these groups are masked or protected by reacting them with 3-pentanone in the presence of an acid catalyst to form a kettle.
So next, I will explain about the benefits and uses in microbiological and medical. The first user is for antimicrobial properties. Star anise extract exhibits strong antimicrobial activities against a broad spectrum of bacteria and fungi. This is inhibiting growth of pathogens such as E. coli and Staphylococcus aureus through disruption of cell membrane. The next uses is for antiviral activities. Shikimic acid from the star anise is a key precursor in the synthesis of the oseltamivir or Tamiflu. A frontline antiviral drug is used against influenza A and B viruses, demonstrating a direct pharmaceutical prevalence. Other than that, star anise is also used for the traditional medicine. This has been used for centuries in traditional Chinese and Ayurvedic medicine as a digestive aid, carminative, and remedy for respiratory infections, cough, and flu symptoms due to its bioactive compound. And the last one is for the drug precursor source. Shikimic acid isolated from the star anise serves as a critical biosynthetic intermediate and industrial starting material for producing antiviral pharmaceuticals and other bioactive compounds in modern drug synthesis. Flavoring industry is also one of the uses in industrial and environmental, such as the star anise oil is rich in transanethol, which is widely used as a natural flavoring agent in food, beverages, and liqueurs. Its intense anise-like aroma make it a valued ingredient in culinary and food processing industry globally. Other than that, star anise is also used in the fragrance industry. Anethol extract from the star anise is a key component in the perfumes, soap, and cosmetics. It serves as a precursor for synthetic masks and other aromatic compounds. Its pleasant, sweet scent make it a highly demand after in the personal care and perfumery sectors. For the sustainable production, shikimic acid from the star anise is a renewable bio-based starting material for synthesizing bioactive compounds, bioplastic, and pharmaceuticals. This support green chemistry initiative by the reducing reliance on petroleum-derived feedstocks in chemical manufacturing. Last but not least is the environmental benefits. Star anise cultivation supports biodiversity and ecosystem health. Its bioactive compound act as a natural pesticide and antifungals, reducing the need for the synthetic agrochemicals. The plant also contributes to soil health and provide habitat for the beneficial insect and pollinators.
In conclusion, the study of shikimic acid is important because it serves as a key intermediate in the biosynthesis of many aromatic compounds in plant and microorganisms. Understanding its structure, properties, and biological roles help researchers to develop pharmaceutical, improve agricultural products, and explore various biochemical pathways. Therefore, shikimic acid will remain a valuable compound in scientific and industrial research.